Hello and welcome. My name is Nicole Mollenkoff, and I have shared a short summary of my professional background at the end of these slides. The title of my presentation is Basics of Human Factors Engineering. This is the relevant financial relationship disclosure for this presentation. These are the learning objectives that will be addressed during this presentation. And finally, these are the key abbreviations that will be used in this presentation. So let's begin with a self-assessment question. What is the Stroop effect, and what does it reveal about understanding design problems involved in medication safety? When we return to this question, I will provide the answer and discuss the rationale. I think this quote really summarizes the goal of using human factors engineering for safety and improving medication safety. We cannot change the human condition, but we can change the conditions under which humans work. Many of you have probably heard this quote before. It's from James Reason, who was a professor emeritus at the University of Manchester. As a safety expert, I completely agree with the sentiment. If you stop and think for a moment about our historical approach to safety improvement, we've kind of had some tension between the people approach versus the systems approach. In the past, a lot of our efforts to improve safety and quality have focused largely on the individual, focused on the person, and really have taken that kind of person approach. And essentially what the person approach is all about is an attempt to make people less fallible, or in other words, more perfect. We know this approach is futile, however. It will not lead to meaningful safety improvements. People cannot perform perfectly all the time, especially when they're in a poorly designed system that lacks appreciation for how to best optimize human performance. It really is just a fool's errand to try to make people more perfect. And as I said, it's not going to result in meaningful safety improvements. So I want you to pause and think for a moment about the systems in your organization. Maybe the systems on nursing units or in the ORs or in clinics or in the pharmacy. How reliant are those systems or those processes and tasks that make up those systems? How reliant are they on people doing the right thing? Have those systems been designed with the ways people work best in mind? So that's really what we're going to talk about throughout this lecture. How do we take a look at those systems and really optimize those for human performance? I think this is a great case to demonstrate how important it is for us to change the systems that people work in and to really consider how to optimize the design of those systems to support human performance. So in this case, a nurse accidentally administered vecuronium, a paralytic agent, to a patient with an order for midazolam, a benzodiazepine used for anxiety. The patient was awaiting a scan in the MRI suite and was nervous, so the anti-anxiety med Versed was ordered. The nurse was a floating nurse or a resource nurse, which means she was helping out wherever she was needed. She was asked to go to the MRI and give the medication because there's no one there that was able to do it or willing to do it given the need to monitor the patient. She removed the medication from the automated dispensing cabinet in the unit where the patient came from, which was the neuro step-down unit. And when she did this, the patient's medication displayed on the automated dispensing cabinet screen. She typed in that medication name, but could not find Versed. She was searching by Versed. Obviously, this was because only the generic name was listed, midazolam. So she went to another screen where she could remove any medication, so the override screen, typed in VE, and the first thing that popped up on the list was vecuronium. Versed was not on the list at all, of note. So she removed that product, reconstituted it, headed to radiology with the person that she was training at the time. The medication was administered, and there was some disagreement as to whether the patient needed some monitoring, but due to some misunderstandings, she gave the med, she left. The patient was put into a room awaiting kind of circulation of the dye before the scan could be administered. And so about 30 minutes later, the radiology tech went to get the patient. She was obviously unresponsive, resuscitated, but later expired. So this is a well-known case in the U.S., particularly because of the horrific nature of the case. There were, so many things that went wrong in this case. The manner in which the patient, kind of experienced this error. You all know as pharmacists or pharmacy folks that, or healthcare folks, that this is, a pretty horrific way to die. But in addition to that, the nurse in this case was criminally prosecuted for negligence and was actually convicted. So as I said, maybe you've even heard of this case in some of the other modules in this medication safety certificate. This is the actual vial that was used. This picture is from Discovery from the court case. As you can see, it's a powder for injection. It says paralyzing on the cap. So these are, some opportunities for the nurse in this case to realize that what she was about to give was not correct and could lead to serious harm. However, I'll point out again, every one of us is human. We're all fallible. That means we're never 100% perfect 100% of the time. But the outcome here could have been different. If there was a system designed that could prevent the nurse from making this uniformly deadly mistake, maybe the outcome could have been different. But instead, what we had was a system that was designed to have the person accommodate the system. And what I mean by that is there wasn't really much between the nurse and the system in terms of, preventing that nurse from pulling out a neuromuscular blocker for a patient that wasn't vented without plans for ventilation. There really was nothing there to stop that person other than the person recognizing, I've got the wrong thing in my hand, really reading the label, or, stopping and pausing and looking at the screen. Now, these are things that, we think people should do and we want people to do. And maybe the vast majority of the time they are able to do those things. But again, people are human. They're going to make mistakes. And in this lecture, we'll talk about kind of how people's performance can be degraded by the environment, by the task itself and the design of the task, by communication with others, all these kind of elements of the socio-technical system that can degrade that performance. And so, I'm going to double down on this idea that if we just take a blame approach to this situation, and, we prosecute the person and make this person feel badly about what they did without really looking at the system that person is engrossed in, then we're probably going to see this happen many more times. I would contend that we have to accept that people are human, people make mistakes, and we've got to chart a path forward that's better than this. So my goal for this lecture is that you never say human error is the root cause after this module. That you make it your goal to make it easy for people to do the right thing and very difficult for them to do the wrong thing, particularly in cases like this where the wrong thing is probably going to result in death. So we know the risk with this med. We must design a system to capture that error before it becomes critical. And I'm going to admit up front, this is no easy endeavor, but it is something that we're capable of. So I think in many cases, it's the design of the system that's betraying us. And I would argue that, maybe the design of the system betrayed the nurse in that case I just discussed, and certainly the patient. When you've got design that betrays you, it's almost like you've got to psychologically prepare for this. This is an idea that I heard from my mentor, Mary Burkhart, who is a nationally known safety expert, a medication safety expert to be specific. And what's happening is we've kind of got design that's really optimized for the technology or for the process or the interface, but it's not designed for optimizing the human at that interface. One of the best examples of this are Norman doors. So think about this. How many times have you walked up to a door, you look at it, you think you know how it works, but then you can't open it, right? These are called Norman doors. And if you Google Norman doors, you're going to get all kinds of stuff coming back at you. Some of it really hilarious because we've all done this. We've all encountered these confusing or difficult to use doors, or these doors that give us one clue about how it works, but yet how it actually works doesn't match with those clues. The top example where do you pull it? Do you push it? There's only one way to do this. It's either pull or push. But if you look at both sides of that door, the handles look the same. It really doesn't give you any clues about the proper way to use the door. My personal pet peeve are these bathroom doors like the picture on the bottom, where you go into the bathroom and you activate the door, but there's not really any feedback as to whether you've actually activated it correctly. I know for myself, I've been in these doors where someone's opened the door despite the fact that I thought I had locked it properly. And it's really embarrassing, right? So the design is betraying us. That's really kind of the fundamental issue here. I want you to think about examples from your environment. Think about your EHR. Lots of those are probably coming to mind. Maybe your work environment, maybe your pharmacy or the design of your pharmacy, or maybe some of the technology or some of the tasks, maybe even like a checklist that's used in your work environment. But here's the issue. So some clues that design is betraying us. Difficult to remember how to use the device. And I'm going to use the word device, but know that this could mean technology. This is, really just kind of a stand-in word for any interface. It could be a checklist, it could be a technology, it could be a process, it could be a task. So anytime it's difficult to remember how to use that device or how to follow a protocol, for example. People frequently mix up items because they look or sound alike. I mean, yeah, think about the work we do. That's kind of like an everyday occurrence. Steps to use a device are non-intuitive or overly complex. Frequent refresher training is needed because people, just can't execute that task or, utilize the device properly. Users can't tell what the device or program is doing. Again, think of my example with the bathroom door. I think I know how to work it, but I don't really have any reassurance that what I've done is actually the correct course of action. Alarms or alerts. I think in our work in pharmacy, we get a lot of alerts. Many of them are nuisances as opposed to being helpful. And that forces us into a scenario where we have to look for the needle in the haystack. We have to look for that, one alert, a shift, for example, that actually is important. And then we have to filter through lots of nuisance or non-value added alerts. A sequence of activities is tedious, repetitious, or error prone. And again, thinking about medication safety, those error prone processes, the ones that get people in trouble. Why do we have them designed that way? Why aren't we, stepping back and redesigning those based on what we know about good design? Finding and fixing errors is difficult and or time consuming. So this is a really important concept. If somebody makes a mistake, the system should make it very obvious that you've just done that thing incorrectly. So anytime that the design doesn't give you that feedback that you've done something wrong, or figuring out how to fix it is really time consuming, that's again an indication that we've got a design problem. And I would say another really great place to think about how we can uncover designs that are betraying us are looking at workarounds. If we've got processes or tasks or technologies that are requiring us to do lots of workarounds, adding nodes, putting up little warning signs, this is definitely an indication that the design is not what it needs to be. So the thing about design is that there's lots of data on design. If you think about, these examples of how design betrays us, this is not just in our work environment, right? Human factors issues are everywhere. They're a part of everyday life. We've got smartphones or alarm clocks, controls in like a rental car, for example, finding your way in places like maybe a place you haven't been before, like an airport in a different country. So these things happen all around us. And we all use machines, we all use technology, we all at some point have to read instructions or interpret guidelines. And so there's so much opportunity for us to design these systems to really support people in their doing their best work. Okay, so I'm going to stop and talk about a few examples from healthcare. And again, I'll urge you as I'm talking about these examples, think about your work environment and think about some examples that you can come up with. So anytime that the design relies on training and procedures for safety, it's a huge red flag that you have a potential design issue that can lead to big problems. So this is a lithotripter. This is a device that's used to break up kidney stones. And essentially, I don't know exactly how the lithotripter works, but I believe it uses like sound waves to break it up, or vibration to break up the kidney stone. And then it sucks that kidney stone debris out of the kidneys. And so part of the device here is using this suction, this air suction, to pull that debris out. But we know if we are shooting air into somebody, we can create air boluses, which can result in deadly events. And so the reason I'm sharing this with you, we had an event at our institution, and I was one of the people that worked on the case. And so one of the things that we found was the design of the system allows you to set it up incorrectly relatively easy. So what you see on the left is the proper setup. So you have to thread the tubing from the left to the right. And you can see that there's a little warning sign there telling you how to do that. But it is extremely easy to do it the other way. And in fact, it's almost kind of more intuitive to do it that way because of the way that the tubing is situated on the device. And so they had kind of like signs and sticky notes like, be careful, make sure you put the tubing in correctly. There's that little diagram on the device as well. But here's the thing. If this is deadly, if we shoot air into a patient as opposed to sucking something out of the patient, and we know that that's in many cases going to be deadly, why is this device even able to do that? Right? I think that's the fundamental question. Instead of trying to fit the person to the system and the way that the system was designed, why don't we think about, well, we should make it impossible to do that really dangerous thing. But unfortunately, that's, not how this particular work was designed. There were sticky notes with instructions indicating, hey, you got to be careful. You got to make sure you put the tubing in correctly. And sometimes people don't see those notes. And routinely, that's how we've approached work. We develop policies, we develop procedures, that says you're responsible for setting up the machine properly. You've got to educate techs, for example, to make sure they do this, maybe even put it in annual education. The problem is that's really trying to fit the person to the system as opposed to getting the design to fit the needs of the person. And that approach really fails to address the complexities of the real world as well. Under normal circumstances, most of the time, this does happen correctly. Maybe when you're fully staffed and then we've got well-rested staff, perfectly calm patients who are on time for their visits, right? All the things that kind of make the work we do complex. And so, when those things don't happen, that's what, those added performance shaping factors might lead to somebody setting this up incorrectly. And so that's why that, bad design can lead to bad outcomes. And thinking about that idea of work as imagined, right? So the policies are written kind of under those ideal conditions, but we have to step back and think about what's happening in the real world and recognize that it probably looks very different. This is an example from my past work, what we thought was happening. So in this example, we had a couple pharmacy technicians. They had a big label job at the start of their shift, several hundred labels, and they would, break up the batch. And then each pharmacy tech would go through this batch and figure out how much drug did they need, what supplies did they need to stage, and then they would send that into the clean room. The problem is when you look through this label stack, there was a lot of memory load. The techs had to figure out, how much drug they needed. They had to kind of go through the labels, label to label, add it all up. It created a memory burden. It was definitely mistake prone. And it was actually time consuming. It would take them about 30 minutes to do this. And this was already a pretty tight process where in many cases we had techs working through their breaks, which as you all imagine is just unacceptable, right? So, we thought that this wasn't a very difficult process. Like on its face, it's like, oh yeah, just take the labels and figure out how much you need. But when we actually looked at it, we realized it required some mental math. It had a high memory burden. There was kind of variable amounts of drugs that were needed from day to day. And ultimately, what techs were doing was just kind of ballparking it and guessing. And so that was creating downstream issues. Like I said, the process itself was time consuming and it was time we didn't have to give. It was error prone. There was a lot of variability in terms of how our different techs did the process. And it really led to some unsafe practices. So that's where we start to see, oh, let's look at work as done. Like what's actually happening? How are all the factors built within that system influencing how we actually do the work? And it was really leading to workarounds. I mean, you can look at these pictures and right away, realize this is pretty unsafe, right? Drugs everywhere. They weren't matched up with the correct labels. It's really easy to make a mistake. What the techs were doing was just kind of ballparking what they needed and throwing everything into the bins. So bad design really does make it harder to do the right thing and can lead to those workarounds. And we have to recognize an individual's ability to complete work is influenced by a lot of factors, and some of them aren't readily apparent. I'll address a little later on how we redesign this to make it easier. So, the problem here, though, is that it's really hard to strengthen systems. It's much easier to say, be more careful or be vigilant. It's a lot harder to really step back and design systems differently to support people. I guess a big issue with that is in order to strengthen systems, we've got to be systems thinkers. Systems thinking gives us the tools to develop a deeper understanding of systems, helps us to see the whole, the interdependencies, helps us to recognize that there are multi-directional cause and effect relationships going on. Kind of helps us balance holistic thinking, looking at the system as a whole, as opposed to reductionist thinking. And I think, we have a habit of just looking at the reductionist kind of component, just looking at the very last person, what their contribution to the system was, without really looking back to all the decisions that came before them and all those different multi-directional cause and effect relationships. I like to kind of think of this as the iceberg model. We look at kind of like above the surface of the water. We can see that component, that last event, that last active failure that happened, and we react to that, right? But we've got to look deeper than that. We've got to look at how staff works. How do our staff work within that larger system? Really look below that waterline. Look at the patterns of behavior. Anticipate their patterns of behavior and how that influences how they get their work done. What really leads to those patterns of work? So what are the system structure that are enabling those patterns of behavior? How can we redesign those structures to help people engage in behaviors that will achieve the outcomes we're looking for? And then even going deeper than that, what are the assumptions? What are the beliefs? What are the values that people hold? What are their mental models around, the way that we approach our work? These things are deeply ingrained and they influence how we understand the world. So ultimately, our goal here is to design systems that work for people. We want these systems that to really help people do their best work. We want to design them so that they help people do their best work. As I've mentioned a couple times, unfortunately, we have a history of doing this the other way around, right? We try to fit the people to the system instead of fitting the system to people. So good design makes it easy to do the right thing and makes it hard to do the wrong thing by leveraging technology, reducing distractions, incorporating backups into high-risk processes, or incorporating engineering controls and workflows that reduce unnecessary steps, for example. These are design changes, right? Human factors can act as the integrating discipline to ensure that we're taking a systems-wide approach. The participative nature of human factors ensures that, that collaboration, that understanding, that we really get down to the bottom of that iceberg and we transform the work that we're doing. So human factors, when you hear the word human factor, what do you think? I can tell you when I'm out kind of on the nursing units or in the pharmacy talking to or observing the way that work is getting done, I hear clinicians use the term all the time, kind of colloquially. They use it to kind of mean how people fail, or maybe in a way that, we're kind of blaming people, right? The human factor. It's kind of like, a way to say, be more careful or try harder or stop messing up or follow the rules. But here's the thing, that's not what that's not what we mean by human factors, right? What we actually mean by human factors is this scientific discipline that's concerned with improving human performance by applying the knowledge of human capabilities as well as the limitations to design better systems that help us make fewer mistakes and be more efficient and actually be satisfied with the work that we're doing. When I think of human factors, I love this analogy. I heard this from my colleague Mary Burkhart, who worked with Jim Bajian at the VA National Center for Patient Safety. And, kind of the way they thought about this was human factors is really the core science of safety. Just like microbiology is the core science of infection control, human factors is our core science of safety. It gives us the tools to uncover the ways we work, how we make mistakes, why we make mistakes, and really ultimately how to design a better system that supports people to do their best work. The mantra that we use in human factors is designed to fit the person, not the other way around. And so when we do this, we can decrease errors, we can decrease fatigue, injuries, we can improve staff and patient satisfaction and burnout. We can optimize interfaces like our health information technology interfaces. We can even optimize communication. And so all of these things are going to lead to fewer errors. And I have to say, understanding human factors will change the way you think about everything in your work environment. Human factors has a very rich history. It's a discipline with more than 60 years of history in other industries. There's extensive research data on human performance, an array of systems analysis methods that can be used that are tried and true, and even design standards that we know improve system and human performance. You may have heard some terms like ergonomics. In Europe, the term ergonomics is what's used interchangeably with human factors. You may even heard of terms like usability engineering or applied cognitive engineering. This discipline is used in other highly reliable industries like aviation or nuclear power, spaceflight, computer software, and hardware development. And as I said, it has kind of a very rich depth of data that we can draw upon to develop better systems. It uses a systems-driven approach, draws from a lot of different disciplines, so like psychology, anatomy and physiology, social sciences, engineering, user design, organizational management. These are, if you interact with a human factors engineer, they could be, their original discipline could be in psychology, or it could be in like user-centered design, right? There really is kind of a lot of different disciplines coming together to build on this work. As I mentioned, those different focuses, like some of these folks might focus on physical ergonomics. For example, they might understand how to balance the force of your body and prevent you from falling. Some might focus on cognitive ergonomics, and they're going to be very educated on understanding how humans process information, for example. And they might focus on the design of systems that attract your attention. Some engineers in this space focus more on macroergonomics and really, understanding the different interfaces that humans will within that socio-technical system and need to be able to operate at, right? So these are kind of the three domains of human factors. Physical ergonomics, which is concerned with the human anatomical, anthropometric, physiologic, biomechanical characteristics and how they relate to physical activity. Or cognitive ergonomics, which is really concerned with mental processes such as perception, memory, reasoning, motor response, and how they affect interactions among humans and other elements of the system. And then finally, macroergonomics. This really goes beyond kind of the individual person and how their physical or cognitive abilities contribute to performance. It takes that information and goes beyond that and really is concerned with the optimization of the socio-technical system surrounding that person. This includes things like tasks that the person will interact with, or tools, technologies, the organizational structures and policies and processes around that person. And so the idea here is that we use this information to design systems that meet the needs of humans. We know about physical limitations. We know about physical capabilities. We know, strength or endurance limitations or exertion or reach, how they might affect the way we do our work, or memory limits, or the length of time we can remain alert, knowledge, skills, our ability to differentiate, how that kind of, impacts performance. The bottom line here is we want to use all of that information to really understand what are humans' abilities to perceive information, comprehend information, make decisions, take actions, right? And so that's what human factors theories are concerned with. So let's talk a little bit about capabilities. These are just some examples. So if we're thinking about kind of in that physical realm, capabilities are what make things work, right? People have a remarkable ability to make things work, even despite their limitations. And some of this is, because of the way our brains work, because of the ways our bodies work. So from a physical perspective, our ability to learn and carry out complex sequences of motor tasks or coordination. And so, ideally we would optimize those abilities. Our perceptual abilities, how easy is it for us to detect info when it's in an appropriate format, right? So we know that people have the ability to perceive trended information when it's presented graphically, for example. That's a human capability we should be optimizing. They also have the ability to spatially locate auditory or visual signals. And so again, how are we using that capability to our advantage? From a cognitive perspective, people can, have the ability to perform complex reasoning. They have the ability to understand complex relationships and make diagnosis and problem solve, maybe even adapt to new situations or draw on past experience. And so these are things we want to accentuate and optimize. So let's do a quick example here. So look at this and figure out how many results are out of range. Take a moment to look through this. And I'm going to do this along with you. All right, so I just finished. I came up with one result that's out of range, but it took me a little while. I had to, kind of scan the information, look back and forth between the results and the reference range. I had to kind of keep a mental note of, as I was going down the list, of how many of these were out of range. I came up with one, but you can imagine how it could be easy to make mistakes here, right? This design of this interface is really not optimized for the way people's brains work. The data is not presented in a way that makes it really easy for us to see what the right answer is. But what if we redesign that? So we're going to do that same exercise. I want you to look through the results and figure out which ones are out of range. So here's our second design. You've probably already found the answer, right? Because now we're presenting this infographically. It's really easy to just look at the screen and realize, oh, wait, I've got one result that's out of range. It's not requiring me to remember a lot of information. It's not requiring me to scan and look back and forth. And clearly the design of this interface is really considering human capabilities when it was designed. So let's talk about limitations. So when we think about limitations, these are the things that we want to minimize, right? So again, we can think across physical, perceptual, and cognitive realms. So with physical, we think about things like time and accuracy trade-offs with gross motor tasks, or reach limitations, like how far can you reach for something, grip strength limitations, repetitive motion and injury. This one is really something that I ended up learning a lot about. I was working in the pediatric pharmacy, and we had a lot of IV prep that was manual when I was working there, and we would see repetitive motion injuries with, pulling on the syringe and drawing up that kind of repetitive motion of drawing up meds over and over again. And, sometimes it's not easy to, depending on the volume, depending on the size, holding that product, pulling on the syringe plunger, and it was no surprise that we would have injuries as a result. Perceptual issues, contrast of lettering and background. You've probably all seen slide presentations where there's, kind of like a dark background and then there's maybe some dark font, and it's really hard to see, right? Think about that in our everyday work though as well. Is there, adequate differentiation between objects, or colors or shapes or sounds? Where there are lots of opportunity for things that like look and sound alike, right? I think this is really important when we think about alerts. We've got to have alerts that get our attention, and if there's not good differentiation, that key information really isn't standing out, that can really be a problem. So if we're not minimizing these limitations, it's definitely going to lead to problems in our work. Even things like inattentional blindness. This is primarily considered a perception issue. It kind of directly relates to the failure of a person to perceive a visible stimulus due to a lack of attention on that stimulus. And so I'll talk a little bit later about inattentional blindness, but the idea here is you're focused on one component, but there's some other component in that visual field that you're missing because you're not really focusing on it. And again, if you stop and think about, your work, you've probably got some examples of where this can be problematic. We need to limit that. We need to really minimize that limitation because we know that's part of the human condition. Finally, cognition, how much we can remember, how easily we can find and integrate information, how long we can remain alert at a task, or, what's known as vigilance. These are all things that are limitations. And, we've got to really be cognizant of these limitations when we're designing interfaces. So a couple examples, lack of differentiation. So this is a real, this is real. This happened where I work. We had some medications that were stored in carts in the OR, and anesthesiologists accidentally gave vecuronium, which you see on the right here, instead of giving what you see on the left, which was cefazolin. And, the anesthesiologists, when we talked to them, they're like, wait a minute, why doesn't it say paralyzing on the cap? I noticed that the caps, for, if you look on the left, you see vecuronium and cefazolin. I mean, clearly they're not the same drug, but when they're stored in the cart, they can look very similar, especially if there's no methods of differentiating those products. It is a national standard. It is a standard in the United States Pharmacopoeia that paralyzing agents have warnings on them, that on the cap, on the ferrule, those warnings are in place. And at the time when we noticed this, we reported this, and the problem was fixed. But that was a standard that was in place at the time that, contributed to lack of differentiation. Now, I would argue we got to go way beyond just differentiating these products, right? Because again, depending on the scenario, sometimes people overlook that information, like that case that I shared at the beginning with the nurse who gave the paralyzing agent to the patient that was not intubated. In this case, in our OR, Luckily, the anesthesiologist was doing minute-to-minute evaluation of this patient and was able to rescue that patient. Indeed, that patient wasn't actually intubated, but was able to rescue that patient very quickly, and the effects, weren't catastrophic. Another thing to think about is vigilance. So another example here is, we use that idea of vigilance, and we talk about this all the time, right? When we're responding to errors, we say things like, well, people need to be vigilant. They need to pay attention. They need to really read the label, right? Vigilance, like from my perspective in the world I'm in of human factors, it can be kind of like a bad word in safety spheres. We routinely hear, like I said, about how people need to be more vigilant. For me, when I hear people say, oh, well, they need to be more vigilant, that's a cue to me that we've got a design issue, that we're probably setting people up for failure. And it is a defined term in human factors, this concept of vigilance decrement. The probability of detecting a signal over time does decrease. So this is an example. This is not a healthcare example, but you could easily overlay a healthcare example on this. What's happening here is we've got Navy staff monitoring a radar scope that's looking for enemy ships in the water, for example, right? For us, this might be a nurse or a tech monitoring in the cardiac ICU looking for patients who are starting to deteriorate, for example. But let's just go back to our non-healthcare example. The person that's doing this monitoring, like in the beginning, they're probably really good at it, right? They're looking at this screen and they're looking for these little black dots which indicate an enemy ship. And they're probably good up front. But we know over time, as they continue to do this, there starts to be a decrement. And even in the beginning, they're probably not, maybe completely perfect. They're scanning and sweeping this, picture. They're looking for what sticks out, what grabs their attention. Again, think back to some of those limitations. If you're looking for one thing, you might miss something else. You're not kind of focusing on that. We know from a perception standpoint that our brains do this kind of automatically. This is like outside of our consciousness. And sometimes we're, filtering out certain information and, only some of that information is getting to us. But even, in a kind of pretty basic system like this one, they're probably able to detect those ships, right? See those little dots pop up on the screen. But when we watch people do this, we know over time their performance degrades, right? And you may think to yourself, well, maybe we just need to give the person a break, right? But again, it's still not 100%. My question will be, well, why not just change the interface? Is there something we can do to make it easier for the person to routinely detect the problem they're looking for and improve that human performance on task? The question here is, how do we increase the likelihood that they see what's important? And this is where design comes into play. Another example is working memory. So I shared that example before where, we've got people having to, use their memory to keep pieces of information, and we know that that is problematic, right? People can only hold pieces of information in their memory for so long. Performance shaping factors can kind of come in and degrade that process. And we're really not minimizing limitations when we design our work this way. This is, again, why we see workarounds, why we see problems that kind of crop up in the system. Here's kind of another little exercise that we'll do to really help us see how human perception can be fraught with problems, and how we have to be cognizant of those problems and design the work to account for those problems. So we're going to do a little demonstration here. This is called the Stroop effect. As you can see, there are 3 rows, and each row has different colored boxes in it. So I want you to actually do this activity with me. Hopefully you're in a place where you can do that. So what we're going to do is we're going to say the colors as fast as we can. And again, just please play along with me. So starting at row 1 and going down to row 3. Red, blue, green, yellow. Yellow, red, blue, red. Blue, yellow, red, green. I think I got them all right. And it was, relatively easy thing to do. Maybe you feel the same way. So let's do this again, but this time we've got 2 pieces of information to help us get this right. Red, blue, green, yellow, yellow, green, blue, red, green, red, yellow, blue. I found that even easier because I was reading the information and the color actually corresponded to that. But sometimes our work's not always designed in such a way to make it easy for us, right? So here's our final task. One last time. Now what you've got to do is not say what the word is. You need to say the color of the text, right? So let's try this again. Green, yellow, red, blue, green, blue, red, yellow, blue, red, green, right? So I've done this a lot and I always kind of stumble, especially like when I get to a string where I'm doing pretty well and then the last one I feel like for some reason I struggle. And the reason why is not a surprise. It's because we've got two different inputs coming in, the spelling of the word, but the actual color of the word. And your brain's got to stop and unpack that information. That takes time, that takes effort. And of course, I'd argue, why are we doing this? We are wasting brain resource when we design things this way. Why are we making it hard for people to do the job, right? And that's the point. We try to fight against the natural way the brain works when it would be much more sensible to just change the interface to support how the brain works best. So in our work, we've got to think about times where we get information in a way that makes it harder to recognize those differences and really try to redesign those processes so it's not hard for the end user. I told you I would come back to inattentional blindness. I think this is another great example about perception and really how perceptive issues, how the way our brain works sometimes makes it hard for us to recognize problems. The brain perceives information and this influences our actions and how we act on that information. There's a popular video where there's a group of students or a group of people wearing white t-shirts and they have a basketball. And then there's, in that same group, there are some students wearing black t-shirts. And what the video says you need to do is just look at the people wearing the white t-shirts. Ignore the people with the black t-shirts. So just to look at those white t-shirts, and anytime those people pass the ball, count that. Right? And so you have to count how many times the person in a white t-shirt passes the ball. And we love this video. So when we teach our staff about human factors, we always use this video and we ask them to kind of go through that exercise. It takes about a minute and a half. And then at the end we say, well, how many times did the player in the white t-shirt pass the ball? And, inevitably people have the right answer, or some of the people have the right answer. Not everybody even gets the right answer because again, there's mental math involved. There's kind of memory load involved. So even though they're really focused in on those folks in the white t-shirts, sometimes they come up with the wrong answer. But even more interestingly, there's other things going on in that video that they don't even notice. For example, as the ball is being passed back and forth, at one point there is a person dressed in a gorilla suit that walks into the video, kind of beats their chest and walks away. And a lot of people completely miss this. And the reason why is because that the people are really focused in on one part of the action, and this other stimuli that it is unexpected, they just kind of completely miss it, right? So it goes unnoticed because their attention is focused elsewhere. And so I would, again, urge you to think about errors in your environment. What are things that maybe you've investigated that are kind of inattentional blindness, as it's called, might it kind of explain that situation. There's a really well-known medication error of a nurse who administered an epidural anesthetic intravenously, thinking it was penicillin. And, again, if you, go to the internet and Google, this particular error, you can find a video of her talking about the fact that she looked at the label and she just didn't see what was clearly before her eyes. In her mind, she had what she thought she had, and even when she looked at the label, she just didn't see it. And so those salient, unique objects can go unnoticed. Like, for example, in that epidural, there was a epidural label on the product and she just didn't see that epidural label. So this concept of inattentional bias can help us understand why people overlook information that's right in front of their eyes. So we have to account for the fact that this is part of the human condition, and we need to design in such a way that minimizes that problem from creeping into our processes. So let's talk about the human factors model. So there's this model where we've got this kind of man-machine interface. It's called the man-machine model. Considers those perceptual and cognitive limitations and capabilities and how those influence actions at an interface. Now, by the way, again, I'm saying interface. We think of interface, we think of, maybe like a computer screen, for example. And that's, what I have pictured here on my screen. But it doesn't have to be a computer screen. It doesn't have to be a pump. It could be a piece of paper. It could be a checklist or a task that the person's engaged in. So if we think about the components of the man-machine model, we've got this operator, right, on the left side of the screen. They've got kind of these psychomotor, hands and feet that they're kind of interacting with that display. And then that input is, maybe there are buttons or keyboards, a mouse, a scanner, and that they're using at that interface. And then when they engage in those actions, that display is going to give them back some outputs, right? Some visual outputs, maybe auditory outputs, maybe tactile feedback, etc. And then your senses are going to receive that information. So your vision, your hearing, your touch, etc. That's really, kind of what this model is about, right? So the kind of overarching components of that man-machine model, you've got that operator. It's got to sense what is referred to as this display. They've got to sense those signals that tell them something about the condition or the functioning of the machine. They've got to, perceive that information. Having sensed that, they've got to interpret it, right? So that interface is just one component. There's so much more after you get that information back that you're sensing that then has to happen. The operator has to interpret that information, maybe perform some computation and reach a decision. And in doing so, again, having a number of human abilities, they can kind of perform these kind of higher mental functions, right? Generally, we kind of call this information processing or cognition. Once they reach a decision and perform that cognition step and reach a decision, then they've got to take some action, right? Exercise some kind of control. Again, maybe they have to push a lever or turn a crank or push a pedal or a switch or whatever. And then there's an action that's going to happen, and those controls exert an influence over that machine on that input, which in turn kind of changes the display. And this is kind of a, continuous cycle, right? And so when we stop and think about human capabilities and limitations, we know that there are decision-making biases that we have to consider, limits on attention, limits on perception, limits on working memory. And then, of course, these things can be influenced by kind of the design of that interface, the size, the shape, the color, the texture, the location or grouping of information, the organization of that information, spatial relationships, logical relationships, terminology, symbols, graphics, etc. These are all things that influence how we interact at that interface. Things we have control over, right? Those things at the top, we don't necessarily have control over. We can't control how a person, like that person's brain and how they're, those kind of innate limits on attention or sensory or working memory or decision making. But we can control some of those, aspects of that interface. And that's really where we can positively influence the outcomes. We've got control over those things. So there's a wealth of design data on how to design interfaces to optimize human performance. I'm going to review that in the heuristic evaluation lecture, but I will talk, just briefly about a couple examples here, how we can really change the design to fit the task or the machine to the person as opposed to the other way around. So here's an example, everyday example, right? Think about the design of a cooktop. If you look at these two designs, which one works better? The one on the left or the one on the right? I know in my home, I used to have the one on the left. And when I redesigned my kitchen, or, when we kind of upgraded our kitchen, I looked out for the design on the right, as opposed to the one on the left that I used to have. Because on the left, I would routinely turn the wrong button on because I would think what I thought made sense as to a normal mapping, right? Because, mental models matter. Affordances are just, the quality or the property of an object that defines its use or makes clear how it should or could be used. And people have mental models about kind of, this is like your internal representation of how the world works. It's a way of simplifying complex information into a framework that helps you understand and reason and make decisions. We've got expectations about how things work. We've got prior training that informs how we think things work. Conventions and norms, right? Like how we think a door should work. When we approach a door and the way the handle looks, we think back to our past experience about what we think we should do. Even implied relationships or like kind of the way things are designed, like the way these knobs are laid out. So again, on the left, I would routinely make that mistake. But with my new cooktop, I almost never make any mistakes because look, it really matches my expectations, right? The design of the layout of those buttons matches that real world design of that cooktop. I think we can apply this in healthcare. Think about syringes, right? Think about different types of syringes, IV syringes versus oral syringes, right? Or, nowadays, even neuraxial syringes that, don't have kind of the same design as syringes that would be used for IV products, for example. So we can take advantage of these affordances to help us make sure we do the right thing every single time. Another, going back to that original example I talked about with improving attention capture. So how do we redesign the system to make it more likely that the person's attention or perception will work the way we want it to work, right? So remember our example of the radar scope where we're trying to detect problems with enemy ships. So if we redesign this to really optimize what we know about the way people perceive information, maybe we wouldn't just have them looking at the screen with black dots on it. Maybe we would change the shape of those dots. Maybe we would change the color, or maybe make them blink, right? That's probably going to get our attention a little bit better. Or maybe provide some auditory feedback or even some tactile feedback. So I like to think of an example here. I was recently at an airport gate and I was heading out to an international conference, and someone ahead of me tried to get on the plane, but they were trying to get on the wrong flight. And the gentleman scanned his boarding pass, but instead of that normal beep that we hear, it let out the most obnoxious noise. Everyone kind of turned around and looked. It certainly captured my attention, but most importantly, it captured the attention of the gate agent. The flight I was on was headed to Switzerland, but apparently, because I was close enough to hear what was going on, this person was headed to Australia and got confused about the gate. And that, if it was just that normal beep that we hear, every time a boarding pass is scanned, and what we were telling the gate agent was read the screen, be vigilant, be very careful. Every single time someone scans their pass, look at the screen and read it and look for where they're going. That's probably going to result in some people getting on the wrong flight, right? But in this scenario, it let this big obnoxious sound out and you just couldn't ignore it. And so here with this scope example, maybe those are some things we can do. Maybe we can change the shape and have it beep, right? This might be a better way to capture attention. Or, I don't know, provide some kind of tactile feedback, like smell, right? Like maybe it elicits a coffee smell. That would get my attention, no doubt. Or, maybe even like zap the person. I don't know. This seems a little cruel, but if it's important enough, it would probably work. Now, I'm being facetious here, and again, this isn't even my example. This is adapted from physician John Gosby, who is a human factors expert as well as a physician. So this is his example, but I love it. I think this is the kind of thing we want to teach our staff at the front lines. Tell them about these kind of ideas and help them to, look at their work on an everyday basis and come up with better ways to perform that attention capture so that you do the right thing and don't accidentally do the wrong thing. Another example in decreasing memory load. Here's something we did. So, we had this kind of big chunk list of labels, and instead of trying to ask the techs to keep doing this process where they have to go through and calculate and add things up, and it takes a lot of time, takes a lot of effort, we ended up just programming a report that printed out with the labels that completely eliminated the need to do this. They could just look at this report, they saw the drugs, how many doses they had, and the total volume that they needed. So not only were we wasting time on this, but we were making errors and like leading to workarounds. And just that simple step of removing the need to do that, number one, we think about cognitive issues, it decreased memory load. That for sure was a benefit, but there was lots of other benefits as well. So how information is presented is crucially important. We've got to consider the user's mental model and their expectations for use. We call this affordances. We've got to eliminate conflicts in information presentation, right? Think about that Stroop test. We've got to use understandable, meaningful symbols, use contrast, color, shape to differentiate and draw attention to key information. In terms of like memory load, we've got to support chunking. Think about like telephone numbers. We don't ask people to remember 7 digits. We put it into 2 chunks, 3 and 4 digits makes it a little easier to remember if we have to memorize it at all. Right nowadays we have lots of ways where we don't even have to memorize phone numbers anymore because they're built into the phone. Reducing reliance on short-term memory is a key thing that we should be trying to do. Maximizing attention capture and really supporting people's decision making is kind of what we're ultimately shooting for. So there's lots of different ways we can do this, lots of possible solutions. Look, this is not an all-encompassing list, and it's certainly not, if you kind of look across, I kind of target perception and attention, memory and decision making. Some of these kind of have some overlap. I'm kind of putting the highest level in here that I think it could be effective. But let's look at some of these solutions. Simplification. We talk about this all the time in safety. Simplification is great. If we can simplify interfaces and prioritize critical information, reduce clutter, use simple language and terms, we're going to increase the person's ability to perceive information, right? Also known as like attentional capture. If we look at memory, it's going to reduce memory burden. If we make things simpler, we're reducing memory burden, supporting chunking, right? Reduces hard to remember strings of info. Not giving too many choices. This is going to help with memory burden. And of course, decision making. If we make things simple, it's going to reduce complexity and it's going to enable easier decision making. Differentiation, color, contrast, shape. This is really most important for perception, right? Like I said before, we kind of scan and sweep, and what sticks out is what we're going to see, right? This is all kind of outside of our kind of consciousness. So differentiation can increase the ability to detect those differences. Really important with alerts, really important with alarms. We've got to capture the person's attention. We've got to make it visual, abrupt, salient in order to capture that attention. Things like minimizing distractions. This is where we, kind of think about performance shaping factors. So background interference can be really problematic, especially for capturing attention, or even, if there's a memory burden, distractions can kind of interfere with the ability to keep those pieces in the short-term memory. Definitely want to reduce distractions during critical tasks. Maybe even things like rotating personnel. That came up, when I was talking about the vigilance decrement, right? We know over time vigilance is going to wane, especially in systems that aren't designed well. So, sometimes we do rotate personnel in order to maintain the vigilance as much as possible. Adequate resources. So I think this is important across the board, right? So things like task load division, looking at different performance shaping factors. If people are feeling rushed, if they're not able to adequately engage, their brains to do the work because they're feeling pressure, they're not going to probably perceive information as well, or there may be some memory load issues or even decision making issues. So adequate resources is really important. Checklists are a great tool. Now there's lots of different design of checklists. It really depends on the purpose, but it can be helpful with, drawing attention to things. Definitely helpful in terms of memory, making sure you don't skip critical steps. And, maybe even, to some extent decision making, but really, really important for memory. Just-in-time information. This is really important for memory and decision making, right? So like things like memory aids or order sets, dosing charts. These can be especially helpful in moving knowledge, what we call moving knowledge from the head to the real world. Really supports recognition rather than recall. So you don't have to be kind of concerned with like remembering the information, reduces the memory burden, and allows you to actually think about the process. So the other aspect of this is in decision making. If you've got a big burden on finding information, this can really impact the ability to make decisions. Sometimes you can't find the information you need to make that decision. So checklists can be helpful. Just-in-time information can be really helpful in that way. Automation and technology, this one's hard because this could be anything, right? We really have to think about how is that automation and technology and interfaces designed, but we can design things in such a way to draw attention to what we think is important. We can automate in such a way that we reduce memory burden. We can automate in a way that provides info at the moment you need it to aid in decision making. So that's why I have kind of checks across the board here. Mental models and affordances, this is really important for decision making. Does it match your expectations? Do you see what you're expecting to see? Does it support decisions based on past experiences, right? We get into things like top-down versus bottom-up processing. We're not going to talk about that here, but as you learn more and more about human factors, that's kind of an area where mental models and affordances are really important. Standards and consistency, really important around memory and decision making. Reducing options, reducing memory burden, standardizing in such a way and making things consistent. So it reduces that burden and really streamlines processes such that it reduces memory burden and it really enables decision making. Finally, limits and barriers, like also known as error prevention. These are crucial at almost every level. We've got to force attention to what's important, right? So we've got to design with that kind of error prevention in mind. We've got to decrease memory burden, and if the process is designed to recognize that memory burden is problematic and kind of limits the need for excessive memory burden, that can be helpful in ensuring good human performance, or even warning or preventing mistakes in decision making before they become critical. But before I kind of wrap up, I just want to talk about the macroergonomic system and what we call the socio-technical system. I spent the majority of this lecture talking about kind of interfaces and our physical capabilities and limitations and our mental capabilities and limitations. But those physical and mental capabilities, that's just one aspect. That's the person. But that person is interacting at all these different interfaces, and all these different elements of the socio-technical system are important. So this is the SEIPS model, the Systems Engineering for Patient Safety model, and this is all about work systems and patient safety. And for those of you who are quality folks out there, you may also notice this is really based on Donabedian's structure, process, outcome model, right? And so this model builds on that work to show how important system design is. And so we consider the person at the center of numerous interfaces all day long. The model, as I said, focuses on that work system and how that's linked to patient safety outcomes through work processes. And human factors research has demonstrated in numerous industries, including ours, that performance, efficiency, safety, quality are the result of interactions of people and within this work system. So we got to really focus on these different elements of the socio-technical system. What we want to do is improve human performance and design those different interfaces so that we recognize the physical and cognitive limitations as well as the capabilities, and we design those interfaces to support that. So we've got to consider performance shaping factors at kind of each of those interfaces. User characteristics, so things like education, training, sleep deprivation, these can degrade human performance at any of those interfaces. The work environment, so thinking about the socio-technical system, what is it about the environment that might degrade performance? Light, noise levels, the layout of the work area, maybe a layout that encourages interruptions, for example. We got to think about the team characteristics. So that's really the people interfacing with other people. What are those dynamics like? What's the division of responsibility? How is communication supported and coordination of activities? What are the expectations across teams? The task nature and complexity. Other concurrent tasks. So is there repetition involved? Is there vigilance demanded? What's the workload look like? What's the expertise or to what extent do we have technology built into those tasks, and what do those interfaces look like? And really thinking about kind of concurrent tasks that are happening, and what's that mental demand, and how's that going to influence performance. So let's look at an example. Going back to that case I talked about at the very beginning, the RaDonda case. Thinking about that case, there were so many different human systems interactions at play. And, some of those could have been areas where if we had better design, that error may not have perpetuated all the way to the patient, right? So again, that socio-technical system, and kind of grounding ourselves in that concept of the socio-technical system with people at the center. And so human to human, right? Communication, the impact of the training she was doing. She probably had some divided attention. She was training a new orientee. The communication between the staff in the ICU and the step-down area, and the communication with the MRI staff, and differences in mental models between the two, ineffective communication between the two. We know that was definitely at play. Thinking about the technology and tools, so the EMR interface to the kind of ADC information flow. We know one of the things that was a problem here was that there was an order for midazolam, but it didn't flow to the ADC. And so when she went to the ADC to remove that medication, she couldn't find it on the patient's profile. And that's why she had to go to override. And part of that was, at the time, there was a technology implementation that was occurring, and there was delays between the data flowing from the EMR to the ADC. Now, in her case, the order was actually there, but she was looking for a medication called Versed, not a medication called midazolam. So again, other opportunities there about how we design that. Does it make sense that it just says midazolam? Should it also say Versed? And that's just a ADC interface design issue. The way the drug names display, the way alerts display. Was there an effective alert that could capture her attention and help her to recognize that she had pulled the wrong drug out of the system? And then, of course, the override process certainly lacked error prevention strategy in that process. Thinking about the tasks, right? This nurse went to the MRI suite and manually gave a medication. There was no BCMA built into the process there. And that is a different mental model from what she was used to on her unit, where everything was given with BCMA. So thinking about, that's just one example of a task. But how about monitoring? There was some discrepancy between what the monitoring we would expect and the monitoring that patient actually received, right? And this had to do with a couple of different things. Lack of standardization around how patients are monitored when they're given intravenous benzodiazepines, whether it's in the ICU, the step-down unit, or in the MRI suite, and also just a complete lack of just-in-time information. Think about it. If this nurse had access to that, information at the moment that said, yeah, make sure you're monitoring this patient for the next 5 minutes, or even in this case, if she had scanned this med and it was for a neuromuscular blocker, some information that, wait a minute, this patient's not ventilated or in the process of being ventilated. Why are you about to do this? So that those tasks themselves were not providing adequate information or error prevention. The organization, so culture around technology implementations, and this is where you're zooming out to that like 15,000 foot level. What was really going on with that technology implementation? I mentioned there was a EMR implementation that was affecting information flow downstream to the ADCs and other parts of the medication administration process. And nurses were being told, well, you're just going to have to override meds for now. So this was kind of a standard practice, and, think about the consequences of that. And again, error prevention that was lacking. And then environment, right? So just the layouts of the MRI suite, the unit layout, how they differ, ease of medication administration. These are all things in the socio-technical system that shaped how that work was carried out. And, again, kind of goes back to this concept of making the person accommodate to the system as opposed to making the system accommodate the person, or that user-centered design approach. So, there are a lot of different methods that are used in human factors to determine what these, how these problems are influencing the work. Field observations is definitely one of the biggest ones. So this means going to the work where the work gets done, and observing and looking for problems. Other things like cognitive task analysis, so understanding a task and looking at the kind of cognitive burden that's associated with that task. Simulation, this is, a tool we use in human factors all the time. We'll have folks simulate a process or simulate the use of a technology, and then maybe do some user testing around that, like usability testing. We have a lecture in this module all about usability testing and how that can be useful, especially in medication safety. Or heuristic evaluation. This is where an expert kind of looks at an interface and uses good design principles to evaluate how likely it is that it'll support human performance. Ultimately, these methods, our goal is to really identify problems, analyze those problems, and hopefully design those problems out of the system so that we can support human performance and eliminate or reduce performance obstacles. All right, so let's do our self-assessment question again. What is the Stroop effect, and what does it reveal about understanding design problems involved in medication safety? The whole point of this lecture is to help you see that the brain receives information in a certain way. We don't have control over how our brains work, but we do know that when we get two conflicting inputs like color or the text of a word, that our brains are going to have to stop and unpack that and do some processing, and errors can occur in that step. So this type of conflict can occur with errors related to medication labeling, for example, but you can imagine lots of other ways that this can be problematic. And so, throughout this lecture, I was really trying to help you see, the way that our brains work, the way that our bodies work, and the way that we're, integrated into that socio-technical system. And we've got an opportunity to design that system around the person and really optimize the way our brains work and the capabilities that we know are really useful. And then we've got an opportunity to limit or minimize those limitations that we know are part of the human condition. And so design, smart design can help us do that. So in conclusion, human factors engineering provides a structure and set of concepts to better understand medication safety issues. We can design in such a way that we support people to do their best work, and this is crucial for addressing medication safety issues. Really, what we need to do is design the system to meet the needs of our people. These are the references that were used to develop this presentation. And finally, thank you for your time and participation.